This is Jack Jackson. In this video we're going to talk about higher order derivatives. So we've seen for a function f we can compute its derivative function, which we might denote as f prime of x or d over dx of f of x or just df over dx. But however, realize that f prime of x is also a function, so it also has a derivative of it. So the derivative of the derivative is called the second derivative of the original function. So notice the notation that we have here. F double prime of x is one of the notations for the second derivative. And of course that is the derivative of the first derivative, which is the derivative of f. And notice it here in this notation we have two d's and two dx's. So in the Leibniz notation we write that as d squared over dx squared, or d to the superscript 2 over dx superscript 2. So this means take the second derivative of f. In other words, take the derivative of f and then take that derivative. And again, in Leibniz notation, you can take this f of x out here, just in a more complicated way of writing f anyway, and we can write the f up in the numerator like this. So I know when I was doing this the first time, I was a little confused about why the squares went here. But if you look back at it this way, you can see that we have two d's and two dx's, but only one f. And so that's why the notation is like it is. So this is kind of a mixture of Newton and Leibniz notation. We have Leibniz notation here, the last line. The very first thing is pure Newton notation, and we kind of have a mixture in the middle. But basically we just take the derivative of the derivative for this first derivative. So remember, the derivative is the instantaneous rate of change in the original function, so the second derivative is the instantaneous rate of change in the first derivative, and thus it is the rate of change of the original function. So the first derivative describes how fast the original function is changing. The second derivative describes how fast the rate of change is changing from the original function. So in a similar manner we can define higher derivatives, third, fourth, fifth, sixth, seventh derivatives. So we'll use the Newton notation as f and then superscript n in a parentheses. That's the nth derivative of x. And so that, of course, recursively we can define that as the derivative of the n minus 1 derivative. In Leibniz notation, that's d superscript n over dx superscript n of f of x, or d superscript n f over dx superscript n. So it's kind of like a power. It's not really a power though. It's multiple times that we apply this operation of taking the derivative. So at this point in the course we're going to focus on using first and second derivatives. In survey of calculus we will probably not go much higher than that, maybe none or very, very rarely. But in Calculus 2, we'll do a lot with higher order derivatives, and we may use them a little bit in Cal 1. But we'll use the first and second derivative quite a bit. So let's go on now to talk about how we could take a second derivative and approximate from the table. So let's think about this a minute. How could we go about approximating f double prime from a table? Well, let's see. We know how to approximate f prime. Like we were trying to approximate f prime at 5. We would take a point on either side, say here and here, and use that to approximate the derivative. Well, to approximate the second derivative, we need the derivative on either side of 5. Well, if you look, if we took these 2 points and did a slope formula, we'd be approximating the derivative somewhere between 3 and 5. In fact, somewhere between 3 and 5, that really would be the derivative. Assume this is a differentiable function all the way across here. And so that's our best estimate at halfway between 3 and 5. So if we took those 2 points here at 3 and 5, and their corresponding y's at 2, 1, did the slope formula, that's going to give us f prime at 4. We could similarly do these 2 points here at 5, 1, and 7, negative 5, do the slope formula, and that finds the derivative at 6. So let's go ahead and do that. Actually, you do it now. Come back and we'll check in a minute. Press pause now. Okay, well, you should have done symmetric difference quotients there, just those slope formulas, and there we have the details worked out. Well, now this gives us this table of x's and f primes, and notice they are equally spaced on either side of our point of interest 5, and now we can do the same slope formula using these 2 points to approximate the second derivative. Go ahead and finish it out and come back when you're finished. Press pause now. Well, we're using this, so f double prime of 5 is approximately f prime at a plus h minus f prime at a minus h over 2h, and we're using these 2 points here. So the 2h is the delta x, which is 4 minus 6, which is 2, h is 1, and then we subtract the corresponding things in the top, and we get negative 1.25. Okay, so you use this technique on the next one. Approximate f double prime at 6 from this table using the technique that we just did. When you finish, come back and check your answer. Press pause now. Well, if we use our same technique, we'll basically be using the slope formula here from 2 to 6. So that gives us a delta x of 6 minus 2 is 4 for the denominator. A delta y of negative 2 minus negative 4 is 2 for the numerator. That works out to be 1/2 or 0.5. And where is that going to be approximating? It's going to be approximating the derivative halfway between 2 and 6. So 6 plus 2 is 8, divided by 2 is 4. 4 is exactly halfway between 2 and 6. So there's our approximation of f prime at 4. Similarly, 10 plus 6 is 16, divided by 2 is 8. 8 is halfway between 6 and 10. So to approximate f prime at 8, we take these 2 points. Again, we're using a symmetric difference quotient. So it's 10 minus 6 is 4 for delta x. Negative 1 minus negative 2 is 1 for delta y. That's 1/4 or 0.25. So now we have the point 4, 0.5, the point 4, comma 0.5, and the point 8, comma 0.25. Those are 2 points for x and f prime of x values. Use those 2 points in the slope formula to compute an estimate for f double prime. So that's going to be 8 minus 4 is 4 for the denominator. 0.25 minus 0.5 is negative 0.25 for the numerator. That's actually negative 1/16 or negative 0.0625. And so that's our best estimate of f double prime of 6 from the table.